Kia ora koutou katoa, ko Dean Anderson toku ingoa. I'm hoping that you can see my presentation.
Yes.
Yep, so I'd like to acknowledge, just to start, my co-authors Adrian and Joe. And let me get going here. There we go. Oops. All right, so just following on from Graham's talk, I'm going to talk a bit about abundance indices and relating those to density. Um, and how they're important, because management needs prediction, as Graham was just talking about, because we can't do management everywhere all the time. So for example, if we wanted to protect Kia in a large area, this large polygon area, yellow polygon area in the South Island, um, we wouldn't be able to control the entire area. In fact, if we may only be able to do 1080 in these isolated management zones, but not all every year. So we have to pick and choose where we're going to do management. And we need some basis for making those decisions, because it's an opportunity lost somewhere else if we're doing management where it's not needed. And so our prediction has to be informed. And these indices of abundance using tracking tunnels or chew cards or snap traps or cameras are really useful because they're cost efficient. They can be rolled out over very large areas. Graham just showed some really nice maps, and repeated over time, over seasons, over years, to look at what's going on, to inform our management decisions. But it must be emphasized that measuring density is really the gold standard. But this requires doing mark recapture studies, which are very expensive and logistically complicated. But we have to understand that these indices of abundance emerge from the number of individuals that are on the ground. They're not a direct measurement of abundance itself. And what's wrong way? Um, there are ecological and detection processes that interact with density that give us our abundance data when we go out and collect trekking tunnel data, for example. And so the objective of this study is really to try to understand those ecological and detection processes that interact with density to give rise to the abundance indices, so that we can better understand when we get a measurement of 30% or 60% tracking um, rates, what that actually means in the underlying population. And so to do this, we're going back to alabaster, which has been talked about quite a lot. So I'll be quick over this. Um, uh, we, we did mark recapture studies in these along this elevational gradient from high elevation down to low elevation in these squares, and interspersed were detection transects where we had snap trap and tracking tunnels and camera detection surveys going on, again along the elevational gradients. And so these data were collected about every 3 months over an 18-month period, 20-month period, which began during a mast and went through the period of resource depletion and the crash of rats, which is shown in this slide. This is the rat density over time, predicted rat density in the black line, and this blue line shows sort of the resource availability over time, starting very high and then decreasing. And so it's a really nice data set for comparing or trying to get at these interactions, because we have density, we have detection, we have changing resources and changing density. And so here's a plot of density measured at alabaster against tracking rates, which is a nice little pattern. And we fit a very simple model to that, which looks very nice and tidy and quite cool. But what does it actually mean? What does it mean? what's ecologically going on here? And more importantly, what does it mean for management? If you look at this part of the data, it's pretty clear that if you've got high density of rats, you're going to get high tracking rates. But what's interesting is that at very high densities, say looking out here, we're not at saturation. Not all the tracking tunnels are getting hit, but there's plenty of rats to hit them. So what might be going on is that this is this period of high density rats, but yet the resources are still very abundant. And so the rats have little incentive to chase after peanut butter and foreign objects in the landscape. So in contrast, what's maybe a little bit more concerning is this part of the data, where anywhere from below one rat per hectare to just over two, we can get pretty much any tracking rate, from one from 10% up to over 90%. So that's a little bit more difficult to interpret. And if you look at these two top ones, we're relatively low density, but really high tracking rates. What could be going on here is we're down at the tail of um, at the end of a masting period, after the crash has occurred, resources are depleted. And so you've got a relatively low population, but there's nothing to eat. And so this may be a behavioral response where individual rodents will get on a transect line and run a good portion of the line to get as much peanut butter as they can. So at the heart of our analysis to understand these dynamics, we're using the detection model, the G0 and sigma detection model, which a lot of you will have heard of and be familiar with. And what that is this G0 is the maximum probability. And what it is when a trap is placed, and this whole model is based on detecting a single individual rat with a single device in a single mine. So if that device is placed at the home range center of a given rat, it will, in this case, have a probability of detection of 0.1. But as we move that trap away from the home range center, the probability of detection will decrease. And the sigma parameter, which is related to home range size, determines the rate of this decay shown in the line. And so we know that a lot of species, that density is correlated with home range size, or home range size is correlated with density. So in possums, for example, we found a negative um, relationship where when possum density increases, sigma or home range size decreases. Moving on, we know that sigma or home range size is correlated with our maximum probability of detection, which we also observed in possums. So increasing home range size or increasing sigma, we see a decrease in G0. And the next slide, I'll try to explain this relationship between home range size and G0. So if you look on the left here, if this circle represents a home range of a small home range of a rat with a single device placed at its home range center, it will have a relatively high chance of detecting that individual because the individual will not ever be moving very far away from this device. So we have a relatively high G0 of 0.1. In contrast, if we have a larger home range with a detection device placed at its home range center, the animal will spend a greater proportion of time far away from that device. And so we'll have a lower G0. So this interaction or this correlation between G0 and sigma is shown that here, where you have a high G0 but a low sigma, which causes a steep decline in detection over a very short radius. In contrast, with a large G0 and the correlated home range, you get at the home range, the maximum probability is low, but it covers a much bigger area, has a bigger detection area. And so what we have is density influencing home range size, which influences the maximum probability of detection. And these things interact to give us our detection data, our abundance data from tracking tunnels, snap traps, and cameras. And importantly, the ecological context is important for predicting and understanding density. So population growth, density dependence, relationships, masting or food resource availability, recent control operations, and the possibility for dispersal. So if we predict density, we can then predict home range size, G naught, and get a reasonable range of what to expect in our tracking data, our abundance indices. And so that's the framework for our statistical analysis to understand these dynamics. And it allows us also to then predict out under certain circumstances important for management what density is and propagate these predictions up through to get what a reasonable expectation or reasonable range of tracking data under a given ecological context. And so I've done that here for just in this case cameras and snap traps. And this is just a simple little simulation to show just different patterns. But for example, if the ecological context suggests that there's probably about only 2 rats per hectare, but yet we go out and do tracking tunnels and we find that there we get a 90% tracking rate. Well, that wouldn't be outrageous. And so we, if we go out and measure that, we can't be certain that an eruption hasn't already occurred. But given our information on the ecological context, there's a good chance that this is a growing population, perhaps headed for an eruption, but unlikely already there. And so that's the our approach to analyzing these data. I think I forgot to mention early on that this is a work in progress. So unfortunately, we don't have any results to share with you at this time. So I'll finish up with a summary slide that just to reemphasize that we need field data to inform predictions for management. And these cost-efficient abundance indices are fantastic because we can do them over large areas and repeat them. Having this density study at Alabaster is turning out to be a seminal piece of field work because it's just so informative, and we actually need a lot more of that to test these models under different circumstances. But we have to, even though these are great devices and can be widely spread, we have to bear in mind that these detection rate data emerge from density, from animal movements, food resources, behavior, and the technology. So our next steps are to complete the statistical analysis and then have a mechanism by which we can simulate predicted detection data to test observed field data. Kia ora.
Awesome. Thank you, Dean. Just one quick question for the moment from the chat. How good are well-placed trail cameras for estimating rat density? And you may have actually answered it a bit in your summary slide, but I'll just give you another chance to comment on that.
For trail cameras to estimate density, did you say?
Yeah, yes.
Well, to use trail cameras to estimate density itself, not an abundance index, we either have to use distance sampling So you have to actually get, put posts out that tell you how far away the animal
Mm.
is. And this is quite an established method. Distance sampling has been around for quite a long time, but using cameras to do it's quite new. Um, yeah, so you'd have to use distance sampling methods, or you would have to be able to identify individuals, like
Mm.
spots on a large cat, for example, um, that sort of thing. But for rodents, I think it's probably you would, or you'd probably have to use distance sampling, if at all. But they can be very useful as um, abundance indices, because you can stick them out and leave them out for 3 months or whatever. Um, yeah.
Mm. And a follow-up question to that is, what about lures, bringing them to cameras? And I guess, well, I'll let you
Yes.
comment on that.
Yes. And I think that's yeah, that's very important. I don't think it's particularly useful to have random cameras out without lures. Um, but lures, of course, wear out. Their attractiveness wears out with time.